Okay, anyway, let's get started. Okay, so last week we talked about format string vulnerability, and we're going to spend 3 sessions or 4 sessions on return-oriented programming next. Before we talk about that, I just want to show you this thing. So this is just something I saw on Twitter that day. So someone find a vulnerability in obj dump, which is the tool we often use to find out vulnerabilities in our class, right? So I feel this is funny to show you guys that every software is vulnerable and could be exploited, even the tool we use to find the vulnerabilities or exploit other software. Okay, so today we will talk about ROP or return-oriented programming. We'll talk about the history, the basic idea. Let's see how many examples we can go through today. We probably do not have time for in-class exercise, actually. Personally, I feel ROP is one of the greatest inventions or discoveries. It's hard to tell this is an invention or discovery in binary attacks in the last 15 years. So let's try to understand why ROP is so important. Depending on whether attackers need to inject binary code into the victim's address space. So far, we have seen 2 types of control flow hijacking attacks. The first type is called code injection attack, in which the attacker needs to first inject some machine code, binary code, then try to subvert the legit control flow of the legit program. So the victim program can execute the injected malicious code. So we have been doing this a lot in the buffer overflow examples. We inject the share code can print out the flag, and we find some buffer overflow vulnerabilities and try to execute that share code. So for a stack-based buffer overflow vulnerability, we also have discussed other places we can inject share code. Most of them are also on stack. Share code can be injected on the buffer. It can be injected in the command line arguments. It can be injected as an environment variable. Both those 3 examples are on the stack. So to defeat code injection attacks, modern CPUs and operating systems have the feature called the DEP, Data Execution Prevention, to make sure everything on the stack is not executable. So we also know that security is basically an arms race. When the defenders stops share code injection or share code execution, the attackers come up with some new ideas of attacks. And one of those ideas is called code reuse attack, in which the attacker doesn't need to inject the share code into the victim's address space, but try to reuse what already exists in that address space. For example, return to libc attack, in which the attacker doesn't have to inject any code, only need to overwrite the return address on the stack. On the stack, then hijack the control flow to a libc function, such as system. So in our server, this doesn't work because if you create a new process, the new process doesn't have the privilege. But on other older machines, return to libc does work. Hold on, let me close my stack here. Okay, sorry about that. So, but a return to libc attacks also have some limitations, not the one we have on the server. For example, the attacker can only return to an existing function. The attacker cannot run arbitrary code, as we can simply by injecting shellcode. So return-oriented programming is a much more generic form of return to libc attack. After return-oriented programming ROP, there was also an idea called jump-oriented programming. That's a similar idea, which we're not going to cover in our class. We will only cover ROP, which will already take us like 3-4 sessions. A little bit of history of ROP. So the technique, not a very generic version of this technique, was first introduced in 2005 to work around the 64-bit architecture that require parameters to be passed using register. Okay, so like in return to libc, or if you want to call return to a function in the address space with parameters, in 32-bit architecture, what you do is you override the stack. You override the parameters at the correct location. But a 64-bit version, if the vulnerability only allow you to override the stack, you still cannot call that function or return to that function with correct parameters, because the parameters are directly stored in registers. So back in 2005, this Kramer, I don't really know that's his first name or last name. So he had the idea of kind of like the return to libc to use code gadgets to set up registers. So you can set parameters for return to libc attacks. Then in 2007, the most generic version of RawProtect was proposed, and in a paper. If you remember, CCS is one of the top venues for cybersecurity. There are 4 top cybersecurity venues. CCS is one of those. So back in 2007, there was a paper titled "The Geometry of Innocent Flesh on the Bone: Return into libc without function calls on the x86" by a professor from UCSD. So this professor, it's really hard for me to pronounce names. Havak Shachen, I can say. So he is a professor who made a lot of contributions in many cybersecurity areas, from crypto to system security. He published many papers. I think recently he moved to UT Austin. Maybe in the recent 5 years, he moved from UCSD to UT Austin. So look at the title of the paper, "The Geometry of Innocent Flesh on the Bone." Okay, the title right now sounds a little bit weird, but later when you see how ROP works, everything will make more sense. So this is basically a picture of the professor and also the original paper in CCS. I want to say something interesting is, so when he published this paper, he was already at least a tenure track professor. So he had PhD students working with him, but he decided to publish this paper by himself. So I think he just realized how important this is, what a great deal this is. So he was so excited to finish everything by himself. In this paper, he discussed how to generalize return to libc techniques into something even more powerful. He explains why this attack is feasible in theory, and he also find out this attack is very practical. In his own words, in any sufficiently large body of x86 executable code, sufficiently large, for example, like libc, C library, there will exist sufficiently many useful code sequences. We will take a look at later what code sequences, why they are special. There are many useful sequences that attackers who controls the stack will be able to undertake arbitrary computations. Okay, so in ROP, the attacker still needs to control the stack, means they can override the stack, but they do not have to execute code on the stack. They don't need to. The stack is not executable, but they need to control the return for at least once. Yeah. So this work is very, very important. 10 years after this paper was published, 2017, this paper received the only Test of Time paper award in CCS 2017. Receiving a Test of Time paper award at any top conference is very, very difficult. I probably told you guys, in our department, Professor Marilla Blanton, she also has a Test of Time paper award from CCS. I don't quite remember which year, but she has one. Yeah. So, so one of this week's homework is to read the original CCS paper, but it's quite difficult to read. So just try to finish as much as possible, especially after the class, you already get the idea. Okay, there is actually a rather longer version of this paper published in the most prestigious security journal as well. The journal is called the ACM TSEC. They recently changed their names, maybe 2-3 years ago. They changed them to ACM TOPS. TOPS stands for Transactions on Privacy and Security. So, but this paper is too long. This journal version is like 30-40 pages. Only if you are really interested in this, you can read this. Otherwise, this one is not required. Okay, so that's a history about ROP. Then let's say how ROP really works. Recall that in return to libc, or doesn't have to be return to libc, return to any function in the address space of the victim program. If the functions we are returning to do not have any arguments, so technically we can chain unlimited numbers of functions together. We can call unlimited numbers of functions. Okay. The reason for that is at the end of each function, there is a return instruction. At the end of each function's code, there is a return instruction. That return instruction will pop the return address from the stack to the EIP or RIP, and the attacker can, if the attacker controls the stack, then they can just lay the return address on the stack one by one. Then those functions will be called or returned to one by one. So in ROP, the only difference is that we are not going to return to a function in libc or other functions in the address space. We're not returning to functions. We simply return to some pieces of code gadgets, code sequences that ends with a return instruction. So actually, with the help of ROP, we can train unlimited numbers of functions together, and also unlimited pieces of code gadgets together to do arbitrary computation. Let me check the chat box here to see if there are any questions. Okay, so far so good. Okay, what's going on here? Oops. So in ROP, we just chain chunks of code. We call those chunks of code gadgets together. Those gadgets are not full functions. They do not really have a function prologue or epilogue. They are just some bytes can be interpreted as code in the executable memory. And we chain them together, we weave them together to accomplish our intended objective. The gadgets do not necessarily stored in continuous memory. They actually don't, okay? But each gadget, they end up with a return instruction. The way to chain them together is similar to chain functions with no arguments together. So the attacker needs to control the stack, but doesn't need the stack to be executable. So here you may ask, is it, you may think that isn't it true that we can only find limited numbers of return instructions in a binary because only a function ends with a return instruction. So let's say if we only have 10 functions, then there are only 10 return instructions. Then there are only 10 gadgets. The truth is that's not true. There can be many gadgets, and the reason for that is the return instruction at the binary level, there are 4 possible values. It can be C3, CB, C2 with a C2 with an immediate number, 16 bytes, or CA. So those are just the byte level representation of the return instruction, 4 possibilities. So any byte that has a value of C3, CB can be interpreted as a return instruction by the CPU. For example, that C3 was originally just 1 byte in an address. There is an address, move FF C3 to EAX. So this is a instruction. But if we interpret the instruction doesn't from the beginning, from some other place, that C3 may be interpreted as a return instruction instead of the address or that number there. So it is not that difficult to find those gadgets in the memory. Reasons, first of all, the x86 instruction set architecture is, the instruction set is very dense. Instructions are variable length as well. You have been saying examples so far. There are instructions just 1 byte. There are instructions 10 bytes, right? They do not have the same length. So to prove this to you, we can do a very simple test. Let's say we just run any of the search. Let's first generate some, let's just generate some random data. So in Linux, we can generate data from the random device. Let's see if it works. Okay, it works. So it worked. So the random device will generate some random data for us. So what we do is we just get some random data, put them into a file there. Let's see. And let's get the data out. random. So you can say we generate, oh, that's too short, huh? Oh, so on this machine, looks like the data we're generating is quite slow. Maybe let's wait a little bit. Okay, now we are generating random data. Let's wait a little bit to let the Linux to generate more data for us. So what we're going to do is we are going to use this random data and try to interpret it as instructions to say if they will be interpreted by the CPU as valid instructions. If they are, it will show that how dense the instruction set is. Even some random garbage can be interpreted as valid instructions. Okay, let's say, oh, that's weird. Why it's so slow? Why we're only getting 19 bytes? Oh, so the random data requires probably mouse movement or something. Let me try. Okay, now I'm moving the mouse to generating some random events. Let's say now we stop this. No, still no. Okay, let me just try to generate some random data on my local machine to do that. We just need more data here. Random. Let's do temp random. Okay. Let's just get amount of those. Okay, let's do XXT. Random. Okay, see, on my computer, we generate a lot of data really fast. Okay, now what we're going to do is we can just find an online disassembler. This assembler x86. Yeah, let's use this one. Then we want to just disassemble some data. Let's see. Okay, so we need to. So we can use a C style. Okay, so what we can do is we can do this. Then we just maybe get 7 lines would be enough. Oops, let me get all of this one. And let me get this one as well. Okay, so we have some random data. You saw me generated random data, so you know I didn't cheat here. Then we just put it here. Okay, that's random data. We try to disassemble this, and you can see the first one, it's a valid instruction. The second 2 bytes are not, but after that, then well, a lot of them are valid bytes, right? Valid instructions. So if we just remove the beginning, remove 1 byte. Oh, remove the 1 byte doesn't work. Then let's remove 2 more bytes. Well, still doesn't work. Now it works, right? So not every garbage byte can be interpreted as a valid instruction, but you can say most of them can be. No matter you are doing 32-bit or 64-bit, see? They all can be interpreted as by the CPU as valid instructions. So for this class, there is a tool you guys will use. Is this called the RawProtect tool? This slide shows how to use this tool. We already installed this tool for you on the server. There are also other tools, but we're not going to use them. I just put them on the slides. So if you want to learn them, you know what to look for. Okay, so in this slide, I show you how tools like RawProtect, they can find all the gadgets in the address space. Remember we discussed linear assembly before, in which a tool decodes all bytes consecutively and pass them into a list of instructions. So on the left-hand side, we have the byte sequence. So the byte sequence could just be the garbage we just collect, or it could be some data on the memory. On the right hand side, we have we can disassemble this byte sequence, get them into disassemblies. For example, this byte sequence, we only have 8 bytes. So if we disassemble from the very beginning, the CPU or the disassembly, where say the first byte is the instruction increase EAX, then the next 2 bytes are basically XOR EAX. Then the next 6 bytes is the instruction move EAX and this number. However, if we do not interpret from the very beginning, if the CPU doesn't execute from the very beginning, it will not get those 3 instructions. Let's say it executes from the 5th instruction, which means it jumps to, let's say if this one is a legit instruction, this is how you originally designed your code. If you jump into the middle of one of your instructions, you do not jump into the beginning of the instruction, you jump to the middle of the instruction. Then these 4 bytes will be interpreted by the CPU. The CPU will say, hey, the first byte is AB, not B8 anymore, but AB. And AB is a store instruction to store EAX to some memory location. Then after AB, there is C3. So what is C3? C3 is basically return, right? So originally, the C3 is just a data. It's just an immediate number in your instruction. It doesn't mean any, it doesn't really have a meaning for instructions, but it can be mistakenly interpreted as an instruction, and it can be a return. And something like this, we call a gadget, because we're looking for gadgets we're looking for code sequences with return, then use them as gadgets. Later we will say how that works. Okay, so next, let's say how we can do ROP assisted return to libc or return to any function on x86. Those functions have arguments. So we're going to revisit our Overflow Return 3. This is the source code of it. All of you hacked this one before. So we have but now we're doing the 64-bit version. Previously you did this 32-bit version. So we have a main function. The main function print out the address of print secret. Then calls a valfoo. Valfoo has a buffer overflow problem there. There's a gets. So our goal here is to overflow the return address on valfoo's stack frame to point that return address to print secret. So so this one I don't want you to cheat. I mean, I don't want you to directly put the address into print flag. I mean, that way you can get the flag, but then you will not learn how to do ROP. Okay, so you need to put the address into change the return address to the address of print secret. Then when you get there, in the 32-bit version, you overwrite the stack for those 2 arguments. One is 1, 2, 3, 4, 5, 6, 7, 8. Another one is dead beef. You write them on the stack. For the 64-bit, you cannot write them on the stack. Instead, you have to change the value of RDI and RSI. And let's say how that works. So this is basically what the stack looks like for 32-bit version. For 64-bit version, things are different because the first argument will go to the register RDI directly. The second argument will go to the register RSI. So the function we are looking at, there are only 2 arguments, I and J. I is the first one, So I is RDI, J is RSI. They are not really on stack. So on the left hand side here, I have the disassembly. Right hand side, I have how do we make this ROP work? This one is a little bit hard to explain. So instead of giving you the rationales to explain how we make this work, I will directly give you the exploit here. So so the figure on the right hand side, that's the exploit for the 64-bit. Then let's see why the exploit works. Then from there, we try to generalize this to say if we can make design other exploits which can do all kinds of things. Okay. So let's take a look here. This is a Volfu. This is 64-bit version of Overflow Return 3. Volfu, we can say the buffer's address is RBP -6. You can see from here. So the buffer from the beginning of buffer to save the RBP, notes that it's not EBP anymore, it's RBP, is 6 bytes. So save the RBP is 8 bytes. So this whole part is 14 bytes. There is no stack cookie on this one, so we can overwrite the stack. However, the stack is not executable. So at the beginning of print secret function, this is the beginning of print secret. You can say its address is here. Then there are 2 instructions: move RDI to RBP -8. Remember that RBP minus something means it's a local variable. So there are 2 local variables, RBP -8, RBP -10. However, those 2 local variables are not really I and J. I and J are actually in here, RDI and RSI. Okay, so I didn't really use compiler optimization here. That's why it generates this complicated code, which is not necessary, but that's how the code looks like. So anyway, you can say the I and J was first placed in RDI and RSI. Okay, then it's not, so those 2, they are not really the parameters on stack. If they are parameters on stack, they should be RBP plus something, okay? Not RBP minus something, because RBP points to saved RBP, RBP +8 points to return address, RBP +16, that should be the first argument, right? So this is RBP minus. So those are not really the parameters. The parameters are in RDI and RSI here. So the exploit will look like this. First, we will have 14 bytes of garbage. Then we will have these 5 items. Each of those is 8 bytes. And if after those items, so the first item is the address of a gadget. The gadget is pulp RDI return. Okay. Basically, this gadget has 2 instructions. The first instruction is pulp RDI. The second instruction is return. The second item here is not an address. It's not a gadget. It's just a data. 1, 2, 3, 4. This number. Okay. Then the third gadget is pulp RSI. Then return. Then dead beef. Then the last gadget is the address of print secret. So let's do a simulation here to see how this works. Later, we are going to really construct this exploit and go ahead.
Why is it 14 bytes again?
This part is 6 bytes. The saved RBP is 8 bytes. 6 plus 8. Any other questions? Okay. So we will first simulate how this works. Then later we're going to craft the real exploit and try to hack this on the server. And we're going to debug that so you can clearly see how it works on the real CPU. Okay, let's assume right now our RIP is at here. We are at the end of Overflow. We are going to execute C3, which is the return instruction, return. So the Q doesn't really matter. So this is just the return. So before the return instruction is executed, when there was no attack, we are supposed to point to the legit. The RSP is supposed to point to the legit return address, right? So here is supposed to be the legit return address, which we overwrite with a new address, and that address has a gadget. That address has two instructions, basically pop, RDI, and return. That's it. Those two instructions. So what will happen is now we're going to execute the instruction return. What does return do? Return will pop whatever RSP points to RIP. That means two things. First one is pop, means RSP will move up 8 bytes. Another one, it means whatever RSP points to will be moved to RIP. So after this instruction, what will happen? After this instruction, RSP will point to this 8 bytes of data, doesn't point to the address anymore. And the RIP will have the address of pop RDI, right? So what is the next instruction to execute? The next instruction will be pop RDI. So what does pop RDI do? Pop RDI will pop whatever RSP points to RDI. That's it. So that's why we have the data here. That data will be popped into RDI, right? So after that, RSP moves up 8 bytes, points to here. Then where does our RIP points to? Our RIP will point to the address of return, okay? Because here we point to the address of pop RDI return. We execute pop RDI, the next instruction we're going to execute is return, right? So what does the return instruction do again? So return instruction will pop what RSP points to RIP again and move this up. So after the return instruction, what happens is RSP will point to the data and the RIP will point to the instruction pop RSI, okay? The RDI already set. So you can see the next instruction we're going to execute is pop RSI. So pop RSI will pop this into RSI. So next, our RDI and RSI, oh, here's a typo. This should be RSI. So after this, both RSI and RDI are set to the value we want, right? Then the next instruction we're going to execute is return again. And the return will look at the stack. Now we have the address of print secret. So this now it's the same as we return to a function or return to libc. But those 4 items on the stack already helped us to set up RDI and RSI. Now after that, we will return to print secret. And when we get it into print secret, RSI, RDI has a correct value. So we can pass this check and print the flag. Does that make sense? Does that make sense, everyone?
Professor,
Yes.
I have a doubt.
Yeah,
So how do we get this gadgets like pop RDI in return?
We are going to do that next. Yeah.
Okay.
And right now, does this make sense to you? Let's say
Yeah.
if this is an exploit, does that make sense to you?
Yeah.
Okay. So next one question is, how do we get the gadgets? So this is related to this picture here, right? So let's say you have a big binary, no matter it's your OA executable or or libc. You are just trying to find instruction sequences that end with C3, right? Because C3 is return. So what you can do is you can just develop a disassembler to interpret from every byte, just one by one, okay? Then you can find all the gadgets in the memory space. And a lot of people already developed tools for you. That's why I listed those tools for you, right? So next, let's say, how do we use those tools so you don't need to develop them by yourself? Okay, so to do RawProtect, the exploit, we can use the same approach we have been using. We just write a Python 2, whatever, right? But to make things more trackable, easier for you to understand, I provided this template to you. So this template will generate the same thing you had before. Let me explain this one line by line. The first line basically says we're going to use Python 2. The second line just say, hey, this is a template. The third line, we're just using a library called pack. Some of you use Python, you're familiar with this. Then we create this exploit, and we have some buffer at the beginning. That's a garbage part. Then we just put those items here one by one, then use the pack function to pack that into the correct endianness. The real reason I want to give you the template is by doing this, you can have a comment here, so you know what you are trying to find. So when you develop a RAW exploit, you probably try to first write what kind of gadgets you want, then look for the address of those gadgets. Next, we are going to, so for example here, this is our exploit, right? We have 14 bytes of garbage. Then we have the pop, RDI, and return. This is the gadgets we're looking for. We are going to find its address. Then the second item is just this data. We're not going to, we don't need to look for the address because that's the data, it's not an address. The third one, we look for this address, then data, this address. Note that here we have how many bytes? We have 40 bytes. Those 40 bytes, none of them are instructions. They are all data or address, okay? So the stack doesn't have to be executable. Okay, let's just copy this one and try to do this on the server. We are going to do overflow 34. What I'm thinking today, 64. Okay, let's say let's create a exploit, whatever, just P Python will be fine. Okay, so we just copy this here. I'm not sure if those addresses are correct. Let's just remove them first because we're going to find them. Those may be correct because I updated my slides yesterday. Whatever. Okay, so we need to, because that's Python, right? So we need to make it executable. Okay, let's see if we can run them. Yeah, it will generate the generate the exploit we want with this with this script. Okay, so now we are trying to find the gadgets using the tool I I told you. Let's say, where's the command? Okay. Oops. Okay, let's start with something small first. Let's start. Okay, so this is a tool. You have to use Python 3 to run the tool. This is a tool. You need to give the tool a binary. Then the tool will find the gadgets for you. Let's start with the executable itself. If we execute this, then you can see the tool find 70 unique gadgets for us. Some of the gadgets are jump gadgets, which we're not going to use. We'll only use return gadgets. Yeah, I think there is a command to no job. Yeah. Okay, so there are 45. There are 45 gadgets in the executables code region. Those are the gadgets we can use. But do we have the one we want? What do we want? We want pulp RDI. Oh, there. See, there's a pulp RDI. See. Then we want pulp RSI. Hey, there is a pulp RSI. Actually, those two will be enough. Of course, here's a problem. There is a pulp RSI and pulp 15, pulp R15. But we don't care about the value of pulp 15, right? We don't care. But we need to put something on our stack to make this happen, to use it. Okay, let's try this. Let's say, let me have two terminals here. What I'm trying to max jump p. Okay, let's just use the gadgets we find in the binary itself. Let's do not use the gadgets in the libc. Libc will give us much more gadgets. Okay, for example, let's say, because this is a dynamically loaded program, right? So it will not have the, what's going on? It will not have the libc statically linked with it, and the libc is here. That's a libc. So what we can do is we can use the same tool. Why it's not working? And copy is not working. Let's see. Oh yeah, I actually have it in the slides. So we can use the same tool to find all the gadgets in the C library. As you can see, it takes, not started yet. Let's do no job here. Cannot find the binary. Oh, what's going on? Which one can I find? We just saw that. Why you cannot find it? Which one is this? Another. Oh, that's a little bit weird. Let's say if we just remove this. We cannot find the binary. Oh, this one. Forgot the white space there. Okay, the previous one. There should be white space. Okay, because if we look for gadgets in the C library, we can find 20,000 gadgets. And if you are searching for some gadgets you want, you can just do a grep, and also the tool can help you. For example, let's say we're searching for pulp RDI return. That's a gadget we're looking for. The tool can show, hey, find two of those gadgets. two different locations. We find the gadgets. Okay, but we just saw that actually if we just use a binary, it's doable. So we're not going to use the gadgets in the C library. Let's save that for next class. So now we just want to use the gadgets in the binary itself. We're looking for, we're using which two? Those two gadgets, right? So going back to here, the first gadgets we're looking for is pop RDI return. And on the left-hand side, we can say pop RDI return here. That's our gadgets location. So we just copy it here. That's our gadgets location. The next, we're moving the data to RDI. The third one, we're looking for pop RSI return, and looks like we are not able to find the gadgets like that. Let's say grep pop RSI return. You can say we cannot find a gadgets like that. In this small binary, we don't have a gadgets like that. But we do have, but our real purpose is to pop RSI, right? So we do find another gadget, which is pop RSI, then pop R15 return. So that will be easy. So we just get this address. We go back here. We set this as this, but we know that this one is pop RSI, pop R15, this. Then the next data will be popped into RSI. Then the one after that one will be popped into 15. Right now, we want the address of printf. So that's all we want, right? So which means we need to create basically another item on stack. So let's just have another deadbeef. So both RSI and R15 will be deadbeef after this code gadgets executes. Make sense? But we don't really care about R15. The reason we set R15 is we cannot avoid setting it. Okay. So after that, we go here. We need to get the address of printf, which I provide here for you. So we just copy it here. Okay, that should be correct. So that is our script to generate the exploit. Then let's run that script. Any questions so far? Does this make sense?
How did you like determine the number of zeros to add to the address?
That part is, the whole thing is just 8 bytes, right?
Yes.
So those zeros actually doesn't really matter. Yeah, doesn't really matter because we already defined its queue. I just want them to be aligned. But the whole thing, since it's 8 bytes, this whole thing should be 16 characters. So this is 16 characters.
Okay.
Yeah. Okay. So if we run this, we will generate our exploit. That's basically our exploit. So previously we do that in command line. Now we write a simple script, but basically the same thing. Okay, that's our exploit. Okay, now let's do something interesting. Let's really, let's try this first, right? So how does this one work? We just do a cat, right? We cat this. We try to say if it works. If it works, oh, we don't need a cat. We just generate the exploit and redirect that to the program. See, it works. Now we can get a flag, right? Now let's debug this to understand how it actually works. I want to make the screen a little bit bigger. Is it big enough for you guys? Can you see it? Or do you want to make it bigger? Okay, I think it's probably better. where am I? Okay, let's debug this program. We set a breakpoint at Overflow beginning. Then we run this one. And when we run this, we want to redirect. Ooh, which command should I use? Should be this. I think should be this. Temp p dot. Yeah, so that should be it. Let's try. Okay, now we are. We're in Overflow. Let's just set a breakpoint at the end of Overflow. We continue. Now we are at the end of Overflow. We should already overwrite the return address, right? Because the get is a valuable one. We should have already written the return address. Let's examine that. So right now, so we already execute leave. So RBP doesn't point to the stack frame anymore, but our SP is still, our SP is supposed to point to the return address. So we can examine RSP. Oh, sorry, RSP. Yeah. So RSP. So you can say RSP is here, and this is a value. Does that look right? Doesn't look right. Is that because the way I executed the program? Oh, there is a dead beef. I see the dead beef. But why there's on? But here, why we only have deaf? There's no dead. This one is dead. Dead beef. Looks like we're a little bit off here. Oh, interesting. So what is that? Okay, let me just print that to a file. I'm not sure my syntax there was correct. Let's just print. That's our exploit. Now we go back here. We run. So I know this syntax is correct. Temp E. Yeah, this one is correct syntax. We execute this. We have these. We continue. Now we are here. So we examine where RSP points to. Okay, yeah. So now it looks good. So you say we can examine. Let's examine how many items we put there. We put. Let's examine 10 items there. Then let's go back here to show you our exploit. So you can say the first item we put in there is the gadget's address, which is correct, right? 1393. Okay. The second item is that data, which is 8 bytes. Let's hold on. Let's do not do. We should not use X. We should use G here because each item is 8 bytes. Okay. Now it's better. So the first item is this, correct? The second item is this, correct? The third item is the address of this gadget, correct? The fourth, fifth item are both dead beef. The last item is the address of print secret, right? Okay, now we are at a return. I'm going to step from here. Then we can see how everything works. So right now we are at return. Then we step this. We are going to say, we actually right now, we are in the middle of a function called the libc cut init. But we are not at the beginning of this function. We're not executing this function. We are just executing a gadget of this function. Let's find where that is. So our gadget is 1393. You can see that. So if I do disassemble of this function, this is what this function really looks like. But we are not returning to here. We are returning to the middle of this instruction. See, we are returning to the middle of this instruction. This instruction, oh no, sorry, it's not. It's we're returning to here. So here we have a 1392. 1392 is a pulp R15, but we are jumping to 1393, which is pulp RDI. So we can do this. Let's try. So this one is, which syntax is this? Let's say pulp R15. See if it works. Okay, so you can say pulp R15 is 41F5F. That's its machine code. So if we're doing pulp RDI, I think it should be 5F, right? See, pulp RDF machine encoding is 5F. The real instruction in this function is pulp R15. But if we jump into the middle of that one, we get pulp RDI. When this program was developed, even though it was not developed in assembly, it was not supposed to have pulp RDI there. We just find it here, okay? That's because the instruction set is very dense. So now we are, so then we execute that one. So we are still here. So now we are going to return, right? Now we return, so, we're actually using this gadgets again. Oh, interesting. We're using those gadgets again. This time we're jumping to, we're using those three instructions again. Now we're jumping to the middle of this instruction. We're jumping to 1391, and that will interpret pulp R14 to RSI. So R14, you can see R14, pulp R14 is 41.5E. So obviously pulp RSI will be 5E. That's why if we jump to here, we get pulp RSI, right? That's why we get that's why we can only find a pulp RSI pulp 15 then return. Okay. Now then we do that, we're getting we're setting up RSI, also setting up R15. Then where are we? Now I guess we are in return. Okay, now see, now we are in pointing to the return instruction again, and now right now RSP points to this data, which is the address of the print secret, which is this one. So when we execute again, we get into print secret. That's basically how it works. Make sense? Any questions? Let's see. Well, usually ROP is quite difficult to understand. I mean, looks like you guys are very smart here. No questions? You can ask anything. Everyone is good? We keep moving forward. Okay, so just now we find the gadgets in the executable itself, right? We can also find gadgets in C library because we know when this program executes, the C library will be loaded into memory. And let's see how do we do that. So for that one, we should be able to find pulp RSI gadget directly, so we don't have to reuse that pulp RSI pulp 15. Where's my command? Let's say this is my command. This one, let's go here. Okay, let's just do a grep pulp RSI return. Notice that this is grep, so you have to follow the syntax of that, its outputs. That's why there are two white space. The tool itself also support regular expression actually. Okay, let's see if we can find a gadget like this. Okay, we do find one. We find two. We find two different locations. So this location, we find those two instructions, those three instructions. Well, they are actually the same thing. This is 29, 26, this is 29. So this one is basically this one, but you start from here, right? So we actually find one gadget at this location. But you can look at the location, this address. This is not really a runtime address. That's because this is offset. To find out where this library is really loaded, you can use the tool LDD, then you can run the program. Then since we disable ASR, every time the result will be the same. And it will tell you that the C library will actually be loaded to this address. Okay, so this is address. Then if you give this address to this tool using offset, it automatically compute the runtime address for you. You can also add them by yourself if you want. Let's say we should get the same thing, but just a different address. So now we get the runtime address for this gadget. As you can see, this address is basically the base address where we get from LDD plus the offset address. Let's try this one. So now we want RSI, right? Let's say, so from the right-hand side, so from right-hand side, so this one we do not have pulp 15 anymore. We don't need that, which means we need to remove an item from here. This one we don't need. Then which one we need to change? This one we need to change. This one we're not going to use the gadgets in itself. We're going to use the gadgets in the C library. Then we do the same thing for RDI. Okay, let's use the first gadget. We'll find the gadgets there. Okay, that looks correct. Let's try this again. Let's generate this one. So we go back to the left window. We just cast this one. E to, oh, we should pipe it, sorry. It should give us the flag, let's see. Okay, it works. So you can see, we find the same gadgets at the different locations, and this time not even in the executable itself, it's in the C library. If we debug this, you will see the same thing. Waffle, we run this temp E. We start from here. So now we can examine the stack with RSP. Let's examine like, so we have, I don't know how many, let's do 10. You can see, this is our first gadget's address. That's data. That's the second gadget address, just one data bit. Then the address of print secret. So if we just do SI, we can say now we are getting into a C library function The same library function is called init cache information, but we're just executing. And let's see, what are we executing here? Is it also at the end or is in the middle? I'm just curious. We are, this is a huge function. This is a huge function, and we're looking for the address 1B72. 1B72. Oh, keep moving. What did I do? It's not working. I cannot. Okay, should be able to find now. 1B72. Okay, you can see this time. Oh, it's here. 1B72. Oh, it's the same. It's actually the same gadgets. It's just this time we find the same one in the same library. So you can imagine the second gadgets is also the same. So okay. So if we keep doing that, we're going to get the flag. Well, here we say cannot open the flag is because we're doing GDB. When you debug this, it doesn't have the permission to open that. Okay, does everything make sense? Okay, we still have 5 minutes. Let's have some questions. Alex asked the question, can you use the same gadgets multiple times? Can someone answer this? JSEM said yes. Well, that is the correct answer. You can use the gadget as many times as you want. You're basically just returning to the same address, then keep running. Yeah, no problem with that. Other questions? Okay, how many of you find this one really interesting? Because this is totally different from what we have learned so far. Sanim says this is very confusing. Well, it is. Yeah. I tried my best to explain this one. I also feel this one is sometimes really difficult to explain, but I try my best. You probably want to debug the code multiple times, rewatch the video, and also do the homework. Alex says this is very creative. Like I said at the very beginning, I personally believe this is one of the most important discoveries or inventions in software security in the last, well, it's more than 15 years. Yeah. That's why it get that's why it get the test of time paper award. So that's basically what we're going to discuss today. We only talked about how to set the parameters today. Wednesday, we are going to look at more complicated exploit. We are going to use RAW to develop exploit to capture the flag directly. So in the address space of the victim program, there will be low function called print secret. We are going to use RAW directly to basically construct the share code you had before, open a file and send the file. We're going to do that in RawP. Let's say what else. Okay, I think that's it. More questions? Let's see. Can we always find the gadgets we want? That's a very good question. No, you can say that. You can say that the gadgets are basically predetermined at the compiler time, right? When you write a program, the compiler will generate the instructions. They map to different machine code, binary code. You do not get to choose, right? So you do not really find all the gadgets you want, but that's as an attacker, you need to be creative. It's similar like in the share code, ASCII share code or long zero share code. You will look for different gadgets which have thematically equivalent to achieve what you want to achieve. Does the stack needs to be executable? No. You don't need the stack to be executable, but you do need to override the stack at least one or several bytes after the return address. We will see one example maybe next week. That one, you do not need to write many bytes onto the stack. So basically, the idea is you are going to find a gadgets to change where the stack is. Then you can change the stack to anywhere you want. It doesn't have to be the original stack. Yeah. Okay, if there is no more questions, I see you guys on Wednesday. So Wednesday we're going to have the we're going to have the online course as well. Okay. Okay, see you guys.